Code written by humans is inherently structural, full of nested loops, branches, and deep hierarchies. But a computer's processor reads data in a strict, one-dimensional sequence. The compiler's job is to take those abstract structures and force them into a linear stream of machine instructions. The core of this process is the synthesis phase. Here, the compiler translates high-level source code into a standardized format called intermediate representation, or IR. This architecture uses IR to decouple the language-specific frontend from the hardware-specific backend. This enables retargetability. A single compiler frontend for C generates one intermediate representation, routed through different backends to connect with dozens of machine types. Because this central layer is isolated from the quirks of specific hardware, engineers can use it to perform broad, machine-independent optimizations. To see exactly how this works, we will track a single mathematical expression as it is flattened, type-checked, and mapped into memory. IR acts as the stable pivot point between high-level logic and low-level execution, providing the necessary abstraction for multi-platform compilation. This equation, A equals B times negative C plus B times negative C, is our starting point. The first step of translation builds a syntax tree. Here, operators act as interior nodes, branching downward, while variable operands sit at the bottom as leaves. While logically correct, this basic tree hides a critical algorithmic inefficiency. Look at the sub-expression B times negative C. It appears twice as two separate branches. If left in this state, the processor would calculate the exact same value twice. To eliminate this redundancy, the compiler relies on a directed acyclic graph, or DAG. The algorithm scans the structure and merges identical subleaves, stripping duplicate branches. The defining characteristic is a shared sub-expression node, now having multiple parents pointing directly to it. By routing multiple operational pathways through a single node, the compiler guarantees that the shared sub-expression is computed exactly once. Condensing raw syntax trees into directed acyclic graphs is the foundational structural step required to save processing cycles before the code is ever executed. With the redundancies removed, the compiler must translate this two-dimensional graph into a linear, one-dimensional execution sequence. It does this by generating three-address code, or TAC. TAC enforces a strict limit on how complex a single instruction can be. This diagram shows the DAG dissolving into three-address code. The standard assignment format allows a maximum of 3 addresses per statement, exactly 2 operands and 1 result. TAC instructions can also take simpler forms, like copying a value from one variable to another, or executing an unconditional jump to another line of code. The engineering challenge shifts from translating the logic to determining how to store these flattened instructions in memory. Compilers utilize 3 primary record formats. The first is quadruples. This table displays a quadruple structure. Because quadruples explicitly name temporary variables in the result column, individual instructions are self-contained, making them easy to move around during optimization. Allocating memory for temporary variables takes space. To reduce the footprint, compilers use a second format, triples. The triples table drops the result column entirely. Instead of named variables, it refers to values by the index number of the statement that computed them. While triples save space, they create a constraint during optimization. Because instructions reference specific index numbers, moving one statement requires updating every subsequent reference. The industry standard solution to this problem is a hybrid structure called indirect triples. Indirect triples use a completely separate array of pointers to index the underlying triples. The data remains static, while the pointers do the navigational work. Indirect triples allow compilers to reorder execution logic by simply shifting lightweight pointers, avoiding the heavy data movement required by standard triples. While the code is being structurally mapped, it must also pass through logical validation. This is managed by the type checker. In languages like C or Java, this is static checking, performed at compile time. Languages like Python rely on dynamic checking, validating types at runtime. The type system uses semantic formulas to ensure that the declared type of a programming construct matches what is expected by its context. Take a look at this semantic rule for array validation. For the formula E1 bracket E2, the system checks the variables. If E2 is strictly an integer and E1 is strictly an array, then the expression is valid and assigned type T. The outcome is binary. Either the system calculates and assigns the expected type, or the compilation halts and throws a type error. Concurrently with this type checking, the compiler determines the memory requirements for each valid declaration. Looking at this memory stack visualization, we see the initialization rule. When a procedure starts, the compiler establishes relative addresses using a global offset counter initialized strictly at 0. With each variable declaration, the offset increments based on the byte size of the declared type. These semantic rules enforce logical consistency while mapping the relative addresses where each variable will reside during execution. The final hurdle of the synthesis phase is handling conditional logic and nonlinear jumps. There are two distinct methodologies for translating Boolean expressions into intermediate representation. The first is the numerical method. For standard mathematical assignments, true is evaluated as a 1 and false is evaluated as a 0. The second is the flow of control method, used specifically for if and while statements. Flow of control is highly efficient because it bypasses calculating a numerical value. Instead, it evaluates the condition and executes a jump directly to a corresponding label. But single-pass compilers read code sequentially, which creates a temporal problem. The compiler often generates a jump instruction before the destination label actually exists. Look at this sequence of instructions. The compiler generated a go-to command, but the destination label hasn't been processed yet. The target address remains completely empty. The compiler temporarily leaves the jump target blank, queuing it in an open jumps list. It maintains this active list as it continues parsing. Once the necessary label is eventually defined further down the sequence, the compiler retroactively patches the correct address back into all of the empty slots on the list. Backpatching enables the compiler to maintain the efficiency of a single-pass scan while correctly resolving the targets of nonlinear jumps. This pipeline visualization shows the complete compilation sequence we've just executed. Structurally, directed acyclic graphs mathematically stripped out redundant computations. Then 3-address code flattened that graph into an optimized pointer array using indirect triples. Logically, type checking secured the data widths, while backpatching guaranteed the control flow could jump across the sequence. This structure represents the final intermediate representation, a language-agnostic blueprint, optimized and ready for translation into machine-specific code.